Hi everyone again. Nice to see you all. I mean, we've been here for the past 20 minutes. So, the next speaker for today and the last one, sadly, is going to be Miguel Pinto. He's a PhD student at the University of Lisbon, and today he's going to talk to us about his work on cosmology, matter creation, and regular black hole in non-minimal geometry matter coupling theories.
All right, so hello everyone. My name is Miguel Pinto, as you've noticed, and today I'll be talking about cosmology, matter creation, and regular black holes in non-minimal geometry matter coupling theories. First, I'll be giving a brief overview of these kind of theories, and then I'll be sort of summarizing the existence literature, the relevant existent literature that we have in these kind of theories. And finally, I'll be speaking about two ongoing projects that I am fortunately involved with. So in order to ensure everyone starts on the exact same page, let us start by some fundamental concepts, all right? So apart from the incredible revolution that GR provoked and predictions as well, today, the Einstein's theory is at the core of the so-called lambda CDM model, the standard model of cosmology, as it is assumed to describe gravity at large, very large cosmological scales. In such a model, the universe is assumed to be spatially homogeneous and isotropic, modeled by the Friedmann-Lemaitre-Robertson-Walker metric, and whose content, matter content, consists of the usual baryonic matter and two dark components, cold dark matter, okay, and a cosmological constant, which is assumed to trigger the so-called late-time cosmic acceleration. And although these two theoretical models are very impressive, it is undeniable the presence of some shortcomings in both of them. For example, the lambda CDM does not explain the true nature of both dark matter and dark energy. We just assume that these are two components of the cosmological fluid in order to match with the observations. With the advancements in precision cosmology, it is now more than evident that there is a discrepancy between early and late time measurements of the exact same quantity, the present value of the Hubble parameter, the so-called Hubble tension. And on a more theoretical side and concerning GR itself, it has been demonstrated that GR lacks uniqueness in the sense that there are other gravitational theories that can explain the exact same phenomena as GR, but by resorting to other geometrical quantities, in particular torsion and non-metricity. And this is remarkably referred to as the geometrical trinity of gravity. And of course, these issues could indicate that there are some problems with our theoretical models and therefore the need for new physics. And there are many paths to choose in order to solve these problems, but one of them is to assume that GR is not the final theory of gravity, even at large cosmological scales. And from this perspective, a very promising route, in my opinion, is to modify gravity. And there are very strong reasons to modify gravity. For instance, to explain the dark components of the universe in terms of geometrical quantities, but also to deal with these theoretical issues of GR, such as its non-renormalizability. And furthermore, to provide a more realistic representation of the gravitational fields near curvature singularities, and as a consequence, to set a viable framework for the quantization of the gravitational interaction. And at this point, I want to stress out a very interesting paper by John Donegal. I don't know if I am mispronouncing it, but this John Donegal guy, he basically considered, not for the first time, but considered GR as the lowest approximation of a possible quantum theory of gravity by applying the so-called effective field theory techniques. And he showed that these classical and quantum corrections to GR are actually higher order curvature terms, which appear naturally in many modified theories of gravity. So there's this link between quantum gravity and modified gravity, you know? But how does one modify gravity? Well, an immediate consequence of Love's law theorem is that in order to modify the Einstein field equations and therefore modify how the gravitational interaction is modeled, we can do basically four things. We can add extra fields to the geometrical quantity, to the geometrical sector, sorry. For instance, non-metricity fields, torsion fields, and etc., so on and so forth. Add more than second-order derivatives of the metric, include non-locality, and add extra dimensions, as it happens, for instance, in Kaluza-Klein theories. And these are the strict rules by which one can modify gravity. And first, I'll be speaking about what do we mean by a minimal coupling theory. First, so it won't be very complicated to understand the non-minimal coupling theories. So in a non-minimal coupling theory, geometry and matter sectors are completely separated. Additionally, matter is described by a Lagrangian density that depends on the metric, on some matter fields, and possibly on its derivatives, on its first derivatives. Then the minimal coupling procedure tells us to promote the flat Minkowski spacetime to a more general spacetime G mu nu. Furthermore, the partial derivative is promoted to a covariant derivative that contains the affine connection coefficients. And of course, this happens in the metric formalism, to be more precise. And a clear example of such a theory is the so-called f of r gravity, which is regarded by some authors as the natural extension of GR. Because instead of having just the Ricci scalar, we have a function of the Ricci scalar. Now, in a non-minimal geometry matter coupling, what we have is like cross terms between geometry and matter. So these two sectors are no longer completely separated. That we have some direct terms or terms in the action that directly connect geometrical quantities to matter fields. And a clear example is the so-called f of r Lm gravity, in which Lm is the matter Lagrangian density, which was created by Professor Arcu and Professor Loeb, which is my supervisor. But there are other examples such as f of r T gravity and these further extension to take into account the fact that for radiation, the trace of the energy momentum tensor is zero, then we do not have direct coupling there, so they essentially extended f of r T gravity by adding this extra contribution, the contraction between the Ricci tensor and the energy momentum tensor. Okay, so a very important consequence in these type of theories and all these theories is that it happens that the energy momentum tensor is no longer conserved. And this could, in fact, violate the equivalence principle, which is very strange. And furthermore, as a consequence, an extra force appear that in principle could be an alternative to dark matter in order to explain the galactic rotational curves. But this seems to be already a reason to rule out these theories, right? Because of this violation of the equivalence principle. But there are also valid reasons to oppose this line of reasoning. One of them is to actually say that although it is a very useful tool, the equivalence principle is not one of those very principles of physics. As pointed out by Thibaut Damour, the equivalence principle is just a heuristic hypothesis introduced by Einstein to construct GR. In modern terms, the equivalence principle could also be related to the fact that the only long-range field that mediates the gravitational interaction is just the spin-2 field, which, when excited, gives us the usual graviton. And in fact, in some higher dimensional theories, in the lower energy limit, there are also some theories that can violate explicitly this equivalence principle. In particular, all versions of string theory have this so-called dilatant field, which couples directly to gravity, but in such a way that violates the equivalence principle. So there's this theoretical reason to oppose the line of thinking that, oh, if it's violate the equivalence principle, then there's no way to escape it. But there's also another reason, and this is from the observational side. It has been reported a dark energy, dark matter interaction and the violation of the equivalence principle in one Abel cluster. So, of course, what we call dark energy and dark matter could be related, at least in principle, in terms of geometrical quantities, and therefore we could interpret these results in the modified gravity framework. And here I just put some recent papers / results on the literature. One of them is the thermodynamic interpretation, which was proposed by Professor Arco in 2014, in which he essentially interpret this non-conservation of the energy momentum tensor as an irreversible flow of energy from the gravitational sector to the matter sector, which could, at least in principle, create gravitationally induced cosmological matter creation processes. So there's this irreversible flow of energy from one sector to the other sector. But there are also other interesting results and investigations, such as compact stars, inflationary scenarios, late-time cosmic solutions, and even traversable wormholes. So there's these very interesting papers for you to look at. And speaking of previous works, I take the opportunity to briefly mention three of mine. The first one is the gravitational induced matter creation in scalar tensor f of RT gravity, in which essentially we explore this concept of irreversible matter creation from the gravitational sector to the matter sector. And we have seen that in this theory, we can actually have a late-time cosmic solution without any dark energy involved. And furthermore, we also have a cosmology in which the universe gradually builds up entropy as particles are created. And one very interesting thing to notice is that it is not the particle production rate that gives rise to a late-time cosmic solution. It is actually the inverse. It is the absence of particle production that gives rise to the late-time cosmic solution. And you could see the paper to check it out. The follow-up of this work was to constrain essentially the parameters of our two most general models. And of course, we have done MCMC analysis with the Pantheon Plus and HZ datasets. And we have shown that for one of our models, in particular, this f of RT model 1, actually is more favored observationally than the lambda CDM model according to this corrected Akaike information criteria. Of course, this does not mean that our model is better overall than the lambda CDM model, but it is not bad either, and more investigation should be also carried out. And finally, we explored the exact same issue, but in another modified gravity, in the so-called energy momentum squared gravity. And overall, the results are essentially the same as the first one. So there's this consistency within all these modified gravities, non-minimal geometry matter coupling modified theories of gravity. Now, I'm going to speak about two ongoing works. One is more theoretical than another, so I'll pass this a bit, I'll rush this a little bit, but nevertheless, I'm going into some details as well. So it looks like black holes exist due to Event Horizon Telescope observations, direct observations. However, black holes display some problems. As you may know, the existence of physical singularities, closed time-like curves, and so on and so forth. And one of the reasons we are trying to construct a consistent quantum theory of gravity is to actually deal with these kind of problems, right? However, we still do not have such a theory in our hands. So what can we do about it? One possible solution, or at least one possible approach, is to explore the so-called regular black hole phenomenology, because these are the compact objects that such a quantum theory of gravity aims to generate, right? But since at the classical level, regular black holes are not true black holes because they are not solutions of the field equations in vacuum, we need some matter content to generate such a geometry, okay? And following previous works, we choose to assume that this kind of matter comes from the so-called nonlinear electrodynamics. And in this case, for the case of nonlinear electrodynamics, the trace of the energy momentum tensor is not zero. And this is one of the reasons why we have chosen to work with f of RT gravity. But also in some quantum gravity models, there's this relation between the trace of energy momentum tensor and quantum gravity, because in these models, the trace of the energy momentum tensor appears naturally at the level of the Lagrangian. So there's this curiosity behind f of RT gravity. And we have chosen to work with 2 plus 1 dimensions because it works as a simpler theoretical laboratory rather than 3 plus 1, although it is not a very realistic model. But in 2 plus 1 dimensions, just to briefly mention, there's this very interesting correspondence, the ADS3CFT2, which is a very interesting and important correspondence in the context of string theory. In short, with this work, we are trying to explore regular black hole solutions in 2 plus 1 dimensional f of RT gravity coupled to nonlinear electrodynamics, and this has been done in collaboration with Roberto Maluf from Brazil. In our theory, just to skip a bit, so I'm not going to delve into details, but in this theory, we have these modified field equations, which are, of course, more difficult, more strange than the usual Einstein field equations. And we have also the gauge field equations. And note that by introducing the trace of the energy momentum tensor, the overall structure of the gauge field equations are already modified by its presence, right? Of course, since every theoretical work has a bunch of assumptions, so here they are. In this case, and again, I'm not going to talk about the very specific details, we can discuss it later, but for the f of RT gravity, we have chosen this specific form in which lambda is a negative cosmological constant that can be written in terms of the ADS radius. We have assumed a circularly symmetric metric, and we have assumed that the only non-zero component of the electromagnetic tensor is the electric field. So with these assumptions and by using these modified field equations, we have essentially these 2 equations. And notice that we have 3 unknowns, 3 variables, the metric coefficient function B of R, the Lagrangian of the nonlinear electrodynamics, and the electric field. So we have 2 equations and 3 variables. So in order to have a closed system of equations, we need to assume something, right? And in our case, we have proposed this specific form of the electric field, which essentially generalizes the usual Maxwell electric field for a point-like charge, but also recovers Maxwell and the asymptotic limit, that is, when R tends to infinity. All right? The simplest case is just this one, in which we could recover not only the usual Maxwell Lagrangian, the usual expression for the electric field, but also 2 very important solutions in this context, the so-called charge BTZ solution and the normal BTZ solution. So far, so good. We are consistent with the literature, but
Miguel, got 5 minutes.
Okay. So in the case of GR, the equations are rather simple. And again, we assume the expression for the electric field, which is this one. And by plugging the electric field in these equations, we could obtain a general expression for the Lagrangian and for the metric coefficient function. And with these solutions, we actually could recover some previously solutions studied in the literature, but also generate new ones, which is very interesting. However, not all of these solutions are actually asymptotically Maxwell, which is very problematic. And this happens, for instance, when the case for alpha and beta equal to 2. So as you can see, when R tends to infinity, the Lagrangian of nonlinear electrodynamics does not tend to 0. That is, does not recover Maxwell. Nevertheless, for the sake of consistency, we actually plotted the metric coefficient function in terms of the radial coordinate, just to see the overall looking of the horizons. And as you can see, just like normal classical black holes, we have one event horizon. However, unlike normal black holes, this solution is completely regular. Why? Because both the Ricci and Kretschmann scalars do not diverge at any point of space-time for a different than 0, okay? So the question is, how can the Lagrangian have a Maxwell-like behavior? And then we have to impose some condition, right? We have to impose that the limit of the Lagrangian of the nonlinear electrodynamics when r tends to infinity must be 0. And this condition gives rise to this relation between our parameters, alpha and beta. And these actually make our expressions more beautiful, okay? So we just have two parameters, A, which is a characteristic distance, and B, which is just an exponent. And here I show you some solutions of our study. As you can see, these were already studied in the literature, but our solutions could generate them, and these solutions are new ones. But for the case of f of RT gravity, of course, these are just regular GR solutions. But for the case of f of RT gravity, which is when lambda is different than 0, the case is very complicated. As you can see, just to give you a brief example, for the case of beta equal to 2, we have this expression for the electric field. And these are the monstrous solutions that we obtain for the Lagrangian and for the metric coefficient functions. I'm not going delve into details. We can discuss it later, but these are very complicated nonlinear equations to solve. Finally, since we are at the CosmoVerse Journal Club, I need to talk about something regarding cosmological tensions themselves, right? And in fact, in collaboration with Tiziano Schiavone, we are actually working on trying to approach these cosmological solutions in the context of f of RT gravity. In fact, Tiziano, Gabriele Montani, and Flavio Bombaccino, they actually studied last year f of r gravity in this context. So they tackle the cosmological tension, in particular the Hubble tension, with f of r gravity and the Jordan frame. But here we try to extend this a bit further by using f of RT gravity. Why? Because while one scalar, in particular this, can essentially we can define an effective Hubble parameter by introducing this scalar. The other one, this psi, is non-minimally coupled to matter, to the trace of the energy momentum tensor. And by doing that, we could actually define an effective matter density, which could be related to the so-called sigma 8 tension. And as you can see, just to finalize, here we have the comparison between the expression for the lambda CDM model and for our theoretical model. So just to conclude, I would like to show you here the conclusions, so feel free to read them. And thank you very much once again for having me. It was a pleasure. Thank you very much.
Thank you, Miguel, for your contribution. So.